In this lesson, we will explore some examples of rings, the quadratic fields, and a group of subrings called the quadratic integer rings. Let's begin by looking at quadratic fields. So for now, let's assume that capital D is a rational number that is not a perfect square in the set of rationals. And we're going to just define the field Q of square root of D by the group of all elements A plus B square root of capital D, where A and B are rational numbers. Since D could be positive or negative, we see that this set is a subset of the complex numbers. So for any choice of D, this is a subset of the complex numbers. Then clearly this set is an abelian group under addition, and it's actually closed under multiplication as well. The set is an abelian group under addition, and it's also closed under multiplication. And to see this, we see that if we take two arbitrary elements, A plus B square root of D times C plus D square root of capital D, when you FOIL this out and combine like terms, we would get AC plus BD capital D, and then plus AD plus BC, the quantity, times the square root of capital D, which is, again, in this set. Since A, B, C, and D are all rational numbers, this shows that the set Q adjoined square root of D is actually closed under multiplication. So therefore we see that this set is actually a subring of the complex numbers. And this subring is commutative, and the identity 1 is an element of the set as well. So now we'll show that this set is actually a field by showing that every non-zero element has a multiplicative inverse. So if A and B are not both 0, then we can actually find the inverse of A plus B square root of capital D. And the inverse of A plus B square root of capital D is A minus B square root of capital D, all divided by A squared minus capital D B squared, which is an element of q of square root of d. So to see that this is the inverse, just take the reciprocal of a plus b square root of d and then rationalize it. Rationalize the denominator. Of 1 over a plus b square root of capital D. And we'll see that we obtain this expression. When a and b are not 0, then the inverse of a plus b square root of d exists, and it's an element of q adjoining square root of d. So therefore, since every non-zero element has an inverse and is therefore a unit, the set q of square root of d is a field. Called a quadratic field. So now we're going to look at a subring of these quadratic fields. So initially, we're not letting square root of d be a perfect square in the rationals. So now when we look at quadratic integer rings, capital D is going to be a square-free integer, that is, an integer that has no factors that are perfect squares. So now let capital D be a square-free integer. And let's look at the subset of q adjoining square root of d. Let's look at the integers adjoining square root of d. So this is the set of all a plus b square root of d, where a and b are integers. So then this subset of q adjoining square root of d actually forms a subring. So one can show that this is a subring by showing that it's closed under subtraction and multiplication, and it's clearly not empty because the number 0 is in this set. Now we're going to look at a specific type of integer d. Now let capital D be congruent to 1 mod 4. So these are any square-free integers that are 1 mod 4. For example, 5 or -3. So we can be positive or negative. And let's look at another subset of q adjoining square root of d. Let's consider the subset z adjoin 1 plus square root of d all over 2. So now this is the set of all a plus b times 1 plus square root of d over 2, where a and b are integers. It's actually true that this subset is also a subring of q adjoining square root of d. So we're going to show that it's closed under multiplication. It's actually very easy to, again, to see that this set is closed under subtraction and it is not empty. Well, it's a little trickier to show that it's closed under multiplication. Let's take two arbitrary elements of this subset and multiply them together. A plus B times 1 plus square root of D over 2, multiplied by C plus D times 1 plus square root of D over 2. Then if I multiply this all out, I'll get AC plus AD times 1 plus square root of D over 2 plus BC times 1 plus square root of D over 2, and then plus BD times 1 plus square root of D over 2, the quantity squared. So we're going to rearrange some of these terms, and let's multiply out 1 plus square root of D, the quantity squared. So this equals AC plus, I can combine the second and third terms to give me the quantity AD plus BC times 1 plus square root of D over 2. And now let's multiply out 1 plus square root of D over 2, the quantity squared. So this would give me BD times 1 plus 2 square root of D plus capital D all over 4. Then we're going to do some manipulation in the third term so we can identify this as an element of Z adjoined 1 plus square root of D over 2. I'm going to write this third term as BD. I'm going to distribute this BD, so BD times, I have capital D, and then I have BD times 1, and then plus 2 BD square root of D. Again, this is all over 4. Now the trick I'm going to do is I'm going to rewrite BD in the numerator as 2BD minus 1BD. So now I have BD capital D minus BD plus 2BD. So now in the numerator of this third term, I have two terms with 2BD in it. So now I'm going to break this up, and the first two terms in the numerator have a common factor of BD, so I'm going to factor out a BD from the first two terms, and I'll have capital D minus 1, and I'm going to break this up as one fraction over 4. And then the second two terms, there's a common factor of 2BD, which I'm going to factor out, and so I'm left with 1 plus square root of capital D, again still over 4. But then there's a common factor of 2 in the numerator and denominator of this last fraction. So if I cancel this common factor of 2, then we obtain a term that has 1 plus square root of D over 2 in it. So then I can rearrange this as AC plus the other constant term with respect to 1 plus square root of D over 2 would be BD times capital D minus 1 all over 4 plus, now if I combine the three terms that have 1 plus square root of D over 2 in it, I get the quantity AD plus BC plus BD times 1 plus square root of D over 2. And we see that this is indeed an element of the integers adjoin 1 plus square root of D over 2. And the only justification we need here is in this part right here. D minus 1 over 4 looks like an arbitrary fraction, but recall, we're assuming that D was 1 mod 4. So if D is 1 mod 4, then D minus 1 is a multiple of 4. And so when we divide by 4, we have an integer. So we see that indeed this set Z adjoin 1 plus square root of D over 2 is actually closed under multiplication. And then the easy parts, showing it's not empty and closed under subtraction, combine to show that this is actually a subring of Q adjoin square root of D. Now let's look more deeply into the subrings of Q adjoin D. So now capital D is still a square-free integer. So with respect to the divisor 4, D could be congruent to 1, 2, or 3 mod 4. So it can't be 0 mod 4 because then it would be a multiple of 4, and therefore it wouldn't be a square-free integer. So now we're going to define a ring O, and this ring depends on the choice of capital D. So it's going to be the set of integers adjoin omega. So this is the set A plus B omega, such that A and B are integers. And omega, again, depends on what D is. So if D is 2 or 3 mod 4, then omega will just equal square root of capital D. But if D is 1 mod 4, then omega will be 1 plus square root of D over 2. In either case, O is a subring of the quadratic field Q adjoins square root of capital D. Then this subring O is called the ring of integers in the quadratic field Q adjoin square root of capital D. And the name comes from the fact that the elements of O behave in the quadratic field Q adjoin square root of capital D with many of the same properties. So they behave like elements of the integers behave in the field of rational numbers. Now we've actually seen an example of these rings of integers. So for example, let's look at when capital D is -1. So we obtain O is the set of integers adjoin square root of -1, which we denote as I. So this is the set of elements A plus BI, where A and B are integers. and this is the so-called Gaussian integers. So these quadratic fields and these rings of integers have played important roles in proving statements about number theory. So now we're going to define a measure that we can use to measure the size of elements in the quadratic field. We now define a measure for the size, in some sense, of elements in a quadratic field, Q of square root of capital D. And we call this measure the field norm. We're going to denote this by capital N. So the field norm will actually be a rational number. We can take the field norm of any element of Q adjoining square root of D, and here's how we do it. So N of A plus B square root of capital D will be defined as A plus B square root of D times its conjugate A minus B square root of D. So this will equal A squared minus B squared times capital D, which, since A, B, and capital D are rational numbers, this is a rational number. So we're actually going to use this field norm to find the units of these quadratic fields. So let's look at the field norm again for when D is -1. So when D equals -1, we're talking about the Gaussian integers, and the norm of an element A plus BI will just equal A plus BI times A minus BI, which produces A squared plus B squared. And this is the square of the typical absolute value or modulus of a complex number. So the norm in the field norm in the Gaussian integers actually gives the square of the modulus of the complex number A plus BI, and the modulus is when A plus BI is identified as a point in a complex plane, the modulus would be the distance from A plus BI to the origin. So the field norm gives a square of the modulus of a complex number, and is therefore the square of the distance from A plus BI to the origin in the complex plane. So we can see how this field norm measures the size of an element. The larger the norm, the farther away that element is from the origin in the complex plane. So now we're going to look at the field norm in the quadratic integer rings. But first we mention an important property of the field norm, the fact that it is multiplicative. So it is a fact that the field norm is multiplicative on the quadratic field Q adjoint square root of D. So that is, if you take the norm of alpha times beta, that will be equal to the norm of alpha times the norm of beta for any elements alpha, beta in the quadratic field. And it can also be demonstrated that the field norm, when applied to elements of the quadratic integer rings, is given by the following formula. So further, the field norm on the ring of quadratic integers is given by the following formula. So now n of a plus b omega will equal a plus b omega times the element a plus b omega bar. And in a second I'll describe what omega bar is. This is going to be defined as a squared minus b squared d if d is congruent to 2 or 3 mod 4. But if d is congruent to 1 mod 4, then the field norm actually works out to be a squared plus ab plus 1 minus capital D over 4 times b squared. Again, this holds only when d is congruent to 1 mod 4. And we need to define omega bar as the negative of square root of capital D if D is congruent to 2 or 3 mod 4, and it's equal to 1 minus square root of capital D over 2 if D is congruent to 1 mod 4. So the formula for the field norm again depends on the integer d. But notice that when we're restricted to the quadratic integer rings, that in either case the field norm is always an integer. We see that a squared minus b squared times d, those are all integers, so this expression is an integer. And then in the bottom, a squared is an integer plus ab, those are integers. And recall that if d is 1 mod 4, then 1 minus capital D will also be divisible by 4, and therefore be an integer. And we have an integer times b squared. So in either case, the field norm is an integer. N of alpha is an integer for all alpha in the quadratic integer ring. Now we're going to use this field norm to identify the units in the quadratic integer rings. So it's a fact that alpha is a unit in the quadratic integer ring O if and only if the norm of alpha equals plus or minus 1. So this helps us find all the units in a given quadratic integer ring. So let's look at the forward implication. So let's suppose that alpha is a unit. Then alpha has a multiplicative inverse, and we can say that alpha beta equals 1 for some element beta in O. Then we're going to use the multiplicative property of the norm. Then we see that the norm of alpha times the norm of beta equals the norm of alpha times beta, but alpha beta equals 1, so this is the norm of 1. And then using either formula, we see that the norm of 1 will just equal 1. So look, we have the norm of alpha times the norm of beta equals 1, and since the norm of alpha and the norm of beta are both integers, the only way this is possible if they're both equal to 1 or they're both equal to -1. So since the norm of alpha and the norm of beta are integers, each must equal plus or minus 1. So we see that if alpha is a unit, then the norm of alpha is plus or minus 1. Now conversely, let's suppose that the norm of alpha equals plus or minus 1, where let's write alpha as a plus b omega. Well, then by the formula that I wrote previously for the norm, we see that a plus b omega times a plus b omega bar, which is the formula for the norm of alpha, must equal plus or minus 1. So we see that alpha, which is a plus b omega, times the element a plus b omega bar is equal to plus or minus 1. So therefore, the inverse of alpha, which is the inverse of a plus b omega, must be either plus or minus a plus b omega bar. So we see that alpha is a unit in O. Therefore, alpha is a unit in the ring O if and only if the norm of alpha is plus or minus 1. So now this gives us a concrete way to find units in a quadratic integer ring. So let's look at an example. We're going to start with the Gaussian integers. So let's find the units in the set of Gaussian integers. So now this again corresponds to when capital D is -1. So we want to find all elements a plus bi such that the norm of a plus bi equals plus or minus 1. Well, recall the norm of a plus bi is a squared plus b squared. So the only way for a squared plus b squared to equal plus or minus 1 would be if a squared plus b squared equals 1, because these are a and b are integers. So just by inspection, if we see if a squared plus b squared equals 1, the only possibilities are a squared equals 1 and b is 0, or a equals 0 and b squared equals 1. So in these cases, we see that the only way we can have a unit in the Gaussian integers if a is plus or minus 1 and b equals 0, or a equals 0 and b equals plus or minus 1. So the only units in the Gaussian integers are plus or minus 1 and plus or minus I. That is, the group of units equals plus or minus 1 plus or minus I. Now let's look at another example when d is negative. So we've already looked at when d was the integer -1. So let's not consider that case again. So d is not going to be -1, and further, d is not going to be equal to -3. Then let's find the units in the quadratic integer ring O. First, let's look at the case when d is 2 or 3 mod 4. And let's get an arbitrary element of the quadratic integer ring. Now let's take the norm of this element. So then the norm of a plus b square root of capital D equals plus or minus 1. This implies that a squared minus capital D b squared equals plus or minus 1. But again, d is negative, so a squared minus capital D b squared is always going to be a non-negative integer. So this implies that a minus capital D b squared actually equals 1, since d is negative. And if b is not 0, then the term negative db squared will be greater than 1. So the only way this can have a solution is if a squared equals 1 and b equals 0. Again, this is only possible since negative db squared will be greater than 1 for b not equal to 0. So the only solution would be if a squared is 1 and b would be 0, and then this leads to a equals plus or minus 1 and b equals 0. So we see that the only units when d is negative, not equal to -1 and not equal to -3, and congruent to 2 or 3, the only units are plus and minus 1. Now let's consider the case when d is congruent to 1 mod 4. And let's take an arbitrary element of the ring O. So it's a plus b times 1 plus square root of d over 2. This is the ring O. Now let's look at the norm of this element. So we're assuming that the norm is plus or minus 1. Then the formula for the norm is a squared plus ab plus 1 minus d all over 4 times b squared. and so this norm is plus or minus 1. And if I multiply both sides of this equation by 4, that implies that 4a squared plus 4ab plus the quantity 1 minus db squared is equal to plus or minus 4. And just expanding this a little bit, we see that 4a squared plus 4ab plus b squared minus capital DB squared equals plus or minus 4. And I notice that the first three terms can be factored. So we see that this implies that the quantity 2a plus b squared, which equals 4a squared plus 4ab plus b squared, and then I still have a minus capital D b squared, this would equal plus or minus 4 if the norm was 1, plus or minus 1. But we look at the expression on the left-hand side, this is always non-negative, because 2ab, the quantity squared, is non-negative, and since d is negative, negative capital D times b squared is non-negative. So the only way that this can have a solution is if this whole quantity equals positive 4. Again, this follows because capital D is negative. So now let's consider possible solutions to this last equation. 2ab, the quantity squared, minus capital DB squared equals 4. So since D is congruent to 1 mod 4, then the biggest negative number that is 1 mod 4 is negative 3. So D can't equal negative 3. So the next largest possibility for D is negative 7. So we see that D must be less than or equal to negative 7. Now if B was not equal to 0, then negative DB squared would be greater than or equal to 7b squared. And since b is not equal to 0, this would be greater than or equal to 7, which is definitely bigger than 4. So the only possibility for a norm to be 1 would be if b equals 0. So thus b equals 0, and in the equation at the top we have that 2a, the quantity squared, equals 4. Thus 4a squared equals 4, and divided by 4 we have a squared equals 1, and finally we obtain that a equals plus or minus 1. So the only units in this case for the quadratic integer ring is also plus or minus 1. So to summarize, we see that for any D less than 0, other than negative 1 and negative 3, the only units are plus and minus 1. So the group of units in O is a set containing just the integers plus and minus 1. So we've almost determined all the units for when D is a negative integer, By contrast, it's actually interesting to note that when D is positive, we have a lot more units. It can actually be shown that when D is positive, the group of units in O is always infinite.